Let us find the magnetic torque experienced by a current loop. So we are taking a rectangular current loop. We can call it as ABCD, which is carrying current from top view clockwise direction. And you remember the right hand thumb rule we used for the magnetic dipole moment. It will be what? This is the current direction and this is the magnetic moment. So current is this way. So I have to curl the fingers this way so that magnetic dipole moment is acting downward. So this will be your magnetic dipole moment, which is perpendicular to the plane of the loop. Okay, so this will be the M vector. And I'm taking this side a north pole, this side a south pole. So the magnetic field will be on the plane. Okay, magnetic field will be on the plane like this. So this way. So the angle between magnetic dipole moment and magnetic field is 90 degree, because B vector is on the plane, M vector is downward. So angle is downward. Why it is downward? It can be upward also depending on the current direction. I'm taking the current direction clockwise from top view, so that the curling fingers will give the current direction and thumb will give the direction of the magnetic moment. So M and B are perpendicular to each other. So we are going to make use of Bill sin theta to find the direction of the force on each segment. So here I'm taking, for example, here we are connecting this to the battery here, so that current enters this way here. So current is in this direction, and I told this is a north pole, this is a south pole. So our magnetic field is in this direction. So field and current are perpendicular to each other, because field is this way, current is this way, so perpendicular to each other. So how will be the force? Bill sin 90. Sin 90 is 1, so it will be Bill. Now let us find the direction. Direction, how to find that Fleming's left hand rule, FBA. Okay, force, thumb force, and forefinger field, and this is the current, middle finger current. So current is towards you, field is to the right side, and so force will be downward. So this will be the FBA. Okay, so current is towards you and field is towards right, so force will be acting here downward. So force on this side will be acting like this, downward, which will be mutually perpendicular to IL vector and B vector. You know that Fleming's left hand rule is used for all three fingers mutually perpendicular. So this will be the case. Okay, so this is the current direction, this is the field direction, and this will be the force direction, which will be, all three will be perpendicular to each other. Okay, force F, B I. Okay, current, field, force. How we got it? This way. Current, field, force. Current, field, force. So this will be acting downward. So that is on this segment, Bill. Now coming to this segment, this is the breadth side. In this, current is in this direction, and already we know that the field is also in the same direction. Okay, on the plane. So angle is how much? 0 degree, and sin 0 is 0. So there will be no force on the breadth side, this breadth side. Same thing is applicable on the opposite side, the breadth side, but only thing is here current is towards this side, then current here it is down the other opposite side. So angle is 180 degree. Here it is 0 degree, here 180 degree. But you know that sin 0 and sin 180 both are 0 only. So here also no force. Okay, because IBB sin 0. B, why? Because it is breadth side. IBB sin 0, this IBB sin 180. So both will be what? 0. So there is no force on the breadth side. Now we have left with only one side, that is this side. So here you remember I told current is this way. So naturally after this current comes this way, and here current is this way towards me. So here current is towards me, but field is like this only on the plane. Again the angle is how much? Only 90 degree, because current is on the plane, field is this way. So force will be again Bill sin 90. This also Bill sin 90, it's also Bill sin 90. But only one difference, direction. How will we get the direction? Just see here. Here earlier current, force, field. Okay. Now what is the difference here? Field is not changing. Current is towards me, but force will be upward. Okay. Okay, field, current is towards me, force will be upward. How will it be in this case? If I take here, this is the field direction, this is the current direction towards me, so this will be the force direction. All three should be perpendicular to, all three fingers should be perpendicular to each other. Okay, so if I use my fingers, field, current towards me, so this will be the force. Okay, so both are bill. This is also bill, this is also bill. Then what is the nature? These are equal in magnitude, opposite in direction, and having different lines of action, and hence they will form a couple. You know, couple of forces mean two equal unlike forces acting having different lines of action. So they are having equal and unlike values, and they're having different lines of action because one is acting here, another is acting here. So they're having different lines of action. So how will you find out the torque? You know that F into D. What is D? D is called a lever arm distance or moment arm distance you studied. Okay, so the force, the magnitude of one force, here it is downward and here it is upward. So because of these two, it will get a rotation this way. Okay, anti-clockwise rotation. It will start rotating this way. It will start rotating anti-clockwise. Okay, now how to get the torque direction? Sorry, torque value F into D. F is clear, bill. Now D, what will be the perpendicular distance between these two? Very clear, it is the breadth. Okay, because one force is here and the other force is on this side. It's acting like this. Both are having a perpendicular distance B. Okay, so it will be F into D, that is bill into the breadth. But you know that length into breadth will give you area. So bill into B, L into B is area. So IAB you'll get. Okay, so in the mathematical steps I'll show. So it will start rotating in this manner. This is a special case where what M vector, magnetic moment vector, and B vector are mutually perpendicular to each other. So it will be IAB, torque will be IAB, and if there are n turns this way, it will be NIAB. Okay, NIAB or BINA or NABI, whatever it is, you can say BINA, you can say, remember it as BINA. So BINA will be applicable only if B vector and M vector are perpendicular. You remember NIA, we had a formula. What is it? Magnetic moment. So it can be called as NIAB, BINA or MB, because NIA is M, MB also you can say. Okay, so this is easy, but if there is an angle between M vector and B vector, then it is a little more difficult. That is the next one we will be coming to. Okay.